Hello. From today, we are going to study a new chapter. Chapter 3 is the estimation, and the main purpose of this chapter is to give you a general framework for estimation for different models. So far in the first two chapters, we considered models and assumptions and what happens if they are wrong, and things like that. And so far, I did not say anything about data. So just briefly just data was not a problem there. I did not say how to calculate this object from the data or what happens if you have not enough data, something like that. But from this chapter, the assumptions are not a problem. We are going to study how to use the data and how to use the data to fit the model. So model is given and suppose it is complete, it has no problem. And then from now on the problem is on the data. Again, by the way, these materials are based on Dewey and McFadden survey paper. It was published in 1994, so nearly 30 years ago, but still it is too difficult for you. So what I explain in this chapter and the next chapter are kind of simplified summary of the content in this paper. I will upload this paper to Blackboard, so if you are interested, you need to read it. If you are seriously considering majoring in econometrics, this paper is a must read. Every econometrician has to understand these materials, pretty much the basic. So let's start with the example, linear regression example. And I believe that you learned from Econometrics 1 that the OLS estimator is calculated this way. X, the thick X, is the capital letter, calligraphic letter X is the matrix from the data. So it's n by k matrix, and y is n by 1 matrix of y. Then beta hat is calculated this way. I believe you know what it is. And we are going to think about this. Okay, we know the answer, and maybe you have learned how it is derived, but we are going to generalize this idea, how we can connect the estimator to the model assumptions we had. So this is based on the data. On the other hand, what we have was this as an identifying equation. So we are going to call this identifying equation. So this is from the model. So the expectation is the population expectation. So it is not about finite sample. It is like if you could have an infinite number of observations, then you can calculate these guys. But so it is purely abstract theoretical object, but its counterpart in sample is this. I will give you 3 different approaches to obtain this estimator. First, you may use the identifying equation directly. Or simply, what we can do here is, so you know this equation. So this equation holds under the classical linear regression assumptions. And then, the problem here is, you do not know what is the population expectation is. The population expectation is unknown, so you replace the population expectation with the sample expectation, sample mean. That's it. So replace the population mean with the sample mean. Replace the population mean with the sample mean. And beta is here, so simply take inverse, multiply inverse of this guy on both sides, and you get this. This is the first idea, you replacing the population mean with sample mean. Very straightforward. And second approach, this is maybe what you learned in Econometrics 1, least squares approach. It works for regression type estimators. Simply you would like to minimize the errors, the residuals that arise between y minus x prime beta. So if you try to explain y using x prime beta, their difference is a residual. The residual squared will be minimized. And so maybe you have learned this way, simple sum of squared errors, sum of squared residuals, but you can consider its population counterpart. In theory, you can show that this minimization, the minimizer of this problem is this. So this equation is the first order condition of this guy. So this minimization problem generates a first order condition of this form. So then what you are going to do here is you are going to solve the same problem using the sample, right? So not using the first order condition, but using the minimization itself. So anyhow, if you minimize this, you are going to get the same OLS estimator, right? By the way, so all of the results are the same OLS estimator. So that they are the same because the linear regression model is so simple. So when your model becomes more complicated, like nonlinear, more complicated error terms, then the first approach and the second approach may imply different estimators. So I'm giving you later. You are going to see what happened. And the third possible approach is using the maximum likelihood estimator. So additionally, if you assume that the epsilon is normally distributed, then you can calculate the maximum likelihood function this way, likelihood function this way, and maximize the log likelihood function. Then you are going to get the same OLS estimator. Also, in general, MLE estimator can be different from the least squares estimator, but in this case, they happen to be the same because the model is so simple. Everything is nice. Okay, then so you have seen 3 different approaches to motivate the OLS estimator. Now let's generalize that. The general principles, there are 2 general principles. Before talking about the principles, I'm going to define abstract notation. From now on, everything will become abstract. So we would like to estimate a parameter vector, theta. It's a k-dimensional vector. You may think it as the regression coefficients. And theta 0, as before, theta 0 is the true value, and theta hat is the estimator. And we are going to denote the ith observation as omega I. Omega I. So depending on the model, the omega may be different. For example, in the classical linear regression model, the ith observation is x and y. But when there is an instrument, you have to have x, y, and z. So if you have more variables, all of them should be included in omega, but as I said, it is abstract. So omega is a vector of random variables associated with ith observations, and obviously omega satisfies IID assumption. So it's a general notation. And later, we are going to consider a function. Say function can depend on the data and the parameter. So for example, the log likelihood function depends on data and parameters. So I will use the function g, and general function can be anything. And as you see, omega can be abbreviated, can be omitted. Instead, I will say subscript I for the function g. Then very simple, so simple notation, intuitive notation. So then the randomness, so by the way, g is a function, theta is a parameter, so it's fixed, and all the randomness is coming from omega. So you can take expectation of this function, this guy, the function of omega, then its expectation implies something like this. So you integrate the function using the PDF of omega and take the expectation. So that is simple simple like a general notation. And when I explain the notation now here, I look so obvious and there is nothing new. But in maybe in a few minutes or so, you will get confused. But then think more carefully what means what, and think about this framework. Okay, I'm going to stop the video here, and we'll continue the main topic in the next one.